non-singular but near singular. That's the problem. And so what do? We know the problem now. So we know that if I have, so suppose my last column, z column is approximately 0. And if I were to solve for alpha, there will be problem. So what I need to do is to drop this. Just drop this. No? Drop this. Set everything to 0. Now when you set everything to 0, you have z1, z2 up to zp minus 1. Let's say zp minus 1 is not quite close to 0 anymore. So there's no problem of ill-conditioned matrix. You can then estimate this very nicely, and then you can do a transformation to get better. So that's the idea of principal component regression. Do you get it? You see, this transformation is so useful. It allows us to just, we can concentrate the tumor to ZP, and then we can just cut it out, and that's it. And then you will survive, and then you can go and dance and enjoy life again. Yeah. So, well, this one says what? This one says, if you have a lambda, that is, if your ZP is near 0, that means this is near 0. And so you have a very large inflated, this matrix, your variance will become very large. So, so this one says, variance of beta j also depends on variance of alpha. So if the eigenvalue is small, variance of beta j will also be large. So I think by now we know what to do. So let's proceed. So assume the regressor variables are arranged in order of decreasing eigenvalues. So I have P of them. Now let me just assume, to be more general, instead of the last one, I say the last S eigenvalue are near 0. Okay, last S. That means what? That means all these are 0. I hope my calculation is correct. Last S. P minus this. Yeah. So all these are 0 or near 0. Okay. Then we set all this to be 0. Now, because this Z vector, they are near 0. If you invert the Z prime Z matrix, you will have problem. So we set them equal to 0. And now we are left with a smaller model. But all these Z are now clearly non-zero. Okay? And so there is no more ill-conditioned problem. And you can then find Z prime Z matrix and then estimate alpha 1 up to alpha P minus S. That's it. And then do a transformation. To get back, to get better. So remember, we set all this to be 0. This one you do a usual multiple linear regression on the remaining z components to get it. And then you set 0 for the rest. We set them to be 0. So we got alpha. This alpha is from principal component model. It's from this model here. It's from this model. Because the rest are set to be 0. So how do we get back beta? Well, beta can be obtained by this transformation here. That's how we define the relationship between beta and alpha. Look, this is, so when we substitute, when we introduce T and T transpose beta is alpha. So there's a relationship between alpha and T beta. So if you can find this in a stable manner, you can do a transformation and get beta. All right? So that's the idea. If you think about it, it's not so abstract after all. Yeah? So let's go into the detail and look at this acetylene data. So in this example, we want to know, we have 3 regressors. We can set them at different values. And we want to know the amount of the percentage conversion into this gas here, acetylene, that is useful for welding and so on. So, is there any linear dependency among the regressors? Well, we don't know. Let's find out. So, first of all, we want to fit a second order model with all the quadratic term and interaction terms. So first step, I'm going to scale to unit length, the response, the one I put in the blue rectangle. And then x1, x2, x3, they are all scaled to unit length. Then I calculate x12 and then scale it to unit length. x13, x23. Then x1 squared. And then I also scale it to unit length. So my model now is based on beta 1, x1, beta 2, x2. All these are unit length scale. Okay? That means here. So this is the model finally that I got. x1, x2, x3. x12 is this. x13 is this. Now in the description of principal component regression, I did not mention anything about unit length scale. So the method does not require us to scale the variables, okay? But we do it because this helps to reduce multicollinearity. So we have, so we can now write this as y equal to beta 1 x1. x1 is just x1 unit length scale, and so on. So x9 is x3 squared scale. So we have 9 variables to look at, and there's no beta naught because it's 0 now. And then now we want to check whether there is any dependency or not. And this can be done by finding the eigenvalues of this matrix, x prime x matrix. So let's take a look at this R code. Yeah. So let's just start from here. So I have n sample size. Y is scale, x1 is scale, x2 scale, x3 scale. Then I calculate all the rest. Then I scale every one of them. Can you follow? Yeah. That's what I did. So I scale x12, x13, and then P is 9. So I write that down. So next is I try to find the X matrix. I put them together as a matrix using this array function, and I specify the dimension of my matrix, n times p. P is 9. So what is x prime x? Simple. Transpose of x multiplied by x. So this is a matrix multiplication. How do I find all the eigenvalues, eigenvector? Simple. Use this eigen function. Apply to x prime x. How do I get it? Well, I store the eigenvalues and eigenvector here, called decomposition. And then I can extract all the eigenvectors here into matrix T that we have discussed all the time. This is the eigenvalues. Yeah, these are eigenvalues. So how do we get all the principal components? Very easy. Z is the new regressors. The new regressors are obtained by x times t. Yeah? Now, this is the matrix of xt, or principal components. So all we have to do is to check the columns of this matrix to see if there's any column that is near 0. If there is near 0 vector, then there's dependency. If all of them are quite different from 0, then there's no dependency. You got that? So let's now take a look at Z. So this is the X matrix. You can print it out to see. I relabel them. So this is the first column of the Z matrix, second column, third. X1 times X2 is the fourth column. So I have 9 X columns. But what is of interest to us is the X times T matrix. So this matrix, you can also take a look. Why? Because all the variables, regressors are unit length scale. So this is a matrix of correlation. So you check for high correlation. Yeah. So this is one of them. Remember this Mason data. Even if you cannot find high correlation, there still might be dependency among the 4 variables. So this pairwise correlation is not a foolproof check for multicollinearity. So that you can take a look. But what is of interest is really this x times t. So this is the set of eigenvectors. I don't know if you can see anything from here, but I can print it out to see all the eigenvectors. Actually, eigenvectors here is not so exciting. What is exciting is the eigenvalues. So you print it out in decreasing order, and you can see that some of them are really very small. Yeah? This is like 0.001. So here is not small, beyond here. So the last 4, maybe the last 5, last 3, last 4, they are actually quite small. The eigenvalues here. Yeah, these are quite small. So that shows there is certain dependency among the regressor variables. And if you don't do anything about it, your model is going to be bad. You know, for example, the ordinary least square regression model, we try to extrapolate, we got negative numbers, right? That's the reason why here. Because the X prime X matrix is very ill conditioned because of multi-collinearity or because of dependency among the regressor variables. So what we really need to look is the XT matrix, the Z matrix. So we convert these regressors X to Z, and Z allows us to see dependency clearly. And because the eigenvalues are arranged in decreasing order, so we can look at the last one. Take a look. Is this a near zero vector? This is 0.001, 0.002 is near zero. Yeah? A little bit subjective. Look at here. This is definitely not zero vector. Look, they are all pretty large. Look at this, the second last principal component, also pretty close to a zero vector. So there's evidence of dependency among the regressors. This one also. This one also close, but getting to be further away from the zero vector. So this vector Z phi, the fifth principal component, this one I think is no longer close to zero. So maybe we can consider dropping this one, this one, this one, or this one. So now the question is, I think we have 4 potential candidates that are causing problem. We should drop them. Obviously, I think this one has to be dropped. This one maybe we can also drop. Now, how about this one? A little bit of subjectivity here, but let's try. Let's try to drop one of them and see what happens. Yeah, or we can drop 2, we can drop 3. So this is something you need to do. So, so we have 9 regressors. I'm going to drop this. I'm going to assume this is 0. In fact, I'm going to drop the last 3 for this. I'm going to drop the last 3 because the last 3 are close to 0, as you can see. These 3. I'm not sure about the 4th one, but these 3, they are really quite close to 0. So I drop them. If I don't drop them, they will be, the variance of the regression coefficient will be very large. So I got to drop them. Once I drop them, I don't have a near singular matrix problem anymore. So let's say we set the last 3 to be 0. And then we have a model with very strong principal components. Strong means non-zero, far from 0. Then you can solve this for alpha. After that, you can do a transformation to get beta. Yeah? So once you do the regression, you will get the first 6, and then you set the last 3 to be 0, and then beta obtained using principal component method is T times this. Now, although these 3 are 0, the last 3 here may not be 0, after transformation. So let's say, so how do we do it in R? So I'm doing it using, I don't know if there is a function in R that just do the principal component for you, but I prefer to do it using the first principle so that you can see it. So here, I'm going to drop the last 3. So I will just keep 1 to 6 and call that my Z matrix. Okay? So I have dropped the last 3. Find the Z prime Z matrix. Find the inverse. Find z prime y, solve for alpha, and then set 7, 8, 9 to be 0. Yeah, set them to be 0. These three. 7, 7, 8, 9. Set them to be 0. And then calculate beta. And that is my answer. Calculate beta. That will be my principal component regression coefficient. Okay? So if you do that, this will be your first 6 principal components. As you can see, these are not quite near to 0. And alpha, you get 6 values only. Add 3 more. And then multiply it. This is your beta. So now, we got our regression coefficient using the principal component regression method. What if I, because this method is a little subjective, someone might say the last 4 eigenvalues are actually quite close to 0. So now I do 4. What happened? Well, I keep 5 then. That means I keep 5 of them. Calculate z prime z, z prime z inverse, z prime y, calculate alpha, and then set the last 4 to be 0, and calculate beta. So that's what you get. The last 5, the first 5 principal components. You solve it, you get the first 5, set this last 4 to be 0, and then calculate beta c. Yeah, so here I've demonstrated to you by assuming the last 3 columns to be 0 or the last 4 columns to be 0. So here's a summary. Now, this is beta 1 to beta 9, obtained using principal component regression. This column is obtained by not deleting any principal component. I keep everything, and this is what I get. And this is exactly what you get when you do the ordinary least square regression. It's the same. You get the same thing. Okay? Let me show you. So here I do ordinary least square based on x1 up to x2 and so on up to x3 square. And then I got this estimate. You can check that it is the same. There's no reason why they should be different, right? It's the same as this. So there's no reason why they should be different. I didn't do anything. I didn't delete any principal component. So this will be the 9 regression coefficient if I delete only the last principal component. So you can see the regression coefficient have changed. And what if I delete the last 2? This is what I'll get. If I delete the last 3, this is what I'll get. Last 4, this is what I'll get. So, one way to decide how many principal components to delete is to do it for, let's say, if you're not sure whether it's 3 or 4 or 2, just do it for 1, 2, 3, 4, 5. And then you see some pattern. You can see that it will start to stabilize a little. And then you change again, very drastically. So it is somewhere here, that you can stop. Either you delete the last 3 or the last 4. Because beyond that, things start to change again quite drastically. These are not too good already. You delete too many. Yeah? So it's either here or here. So here I say the regression coefficient seems to have stabilized. And here you remove too many, so that's not too good. So that's one way you can do it. So some final notes. Number one, suppose the multiple linear regression model is this, and we have this. And if there is near linear dependency, x prime x will be near singular, then this will result in large variance. Yeah? What about ridge regression? Ridge regression attempts to reduce this large variance problem by strengthening the ridge. You know, it's strengthening. It's a very simple idea, and it works. It works quite beautifully. And once the x prime x matrix is strengthened, then the matrix becomes less singular or less ill conditioned. You will have more stable estimates of beta. Now, in principal component regression, we convert this model into this. We convert the X matrix into a matrix of principal components. Why? Because the principal components tell us whether there is any dependency or not. If a particular principal component is near zero, then we know there is dependency. You can just drop it because the tumor is very well defined. It's right there, just drop it. And then you can work with the rest of the principal components. After that, you just transfer it back, transform back. Okay, so that's the idea. So in terms of, so it's like you have a tumor, ordinarily square regression say take Panadol, that's how you can solve your tumor problem. Ridge regressions simply say, what do you do? Maybe you don't take Panadol, take something, I don't know what's the comparison, but for principal component regression, it actually operates on the patient, operates on the tumor and remove it. That's the beauty. All right. Well, if you look at the theory, scaling is not required. Okay, you can do without scaling. Why do we scale? Because we can compare them more meaningfully because now they are standardized. And also, we can reduce the effect of multicollinearity. The response variable is scaled along with the regressor variable mainly for one reason. The resulting model has an intercept term that is 0. That's the reason. Okay. All right. Now, what I want to do is to try to explain. So as I've said, someone asked me this question. So lambda small, let's say 1 or 2 or more, let's say lambda small, imply linear dependency. Dependency. Do I get it right? Dependency among regressors. So this is correct because we proved it. So now the question is this correct or not? Okay, so if there's linear dependency, will an eigenvalue or some eigenvalues be small? Well, I say yes. Now, let me look at something let's say small, let me prove something even more than this. Small eigenvalues, 1 or more. Small eigenvalues. So that implies high linear dependency. Okay? Now let's look at this. High linear dependency means what? High linear dependency means the betas have high variances. Okay? So there are three things here. One is small eigenvalues, means high dependency. And then there's this thing, beta have high variances, so estimated poorly. So how are these three things related? Well, can we say that this is true? High dependency means beta have high variances. How do you justify this? High linear dependency means what? Multi-collinearity. Okay. So, well, if there is high dependency, then if there's high dependency, then what happens here is you will have let me just take a look. In other words, you will have this x times, for example, the last one will be close to 0, right? In our study. High linear dependency means one or more of your principal component is near 0 vector. And because of this, your Z prime Z matrix is ill conditioned. When the Z prime Z matrix is ill conditioned, you invert the matrix and then you calculate beta. That means you don't remove any of the principal component. Your beta will have high covariance, high variances. So this is true. So now, can we prove this or not? Or can we argue this is true or not? If I have high variances, does that mean the eigenvalues are small? Well, this is also true. Look at chapter 9a, page 13. Let me write down the result for you. Expected value of the square distance between beta hat and beta can be shown to be variance of beta j, and this is sigma square summation j equal to 1 to p 1 over lambda j. So we show that the expectation of the square distance between beta hat and beta is actually this. So if the total variance is big, that means some of them are big, then some lambda must be big. If some lambda is lambda must be small. If some lambda is small, then the variance must be big. So this is two-way. This result is actually two ways. So because of this, I can actually, so variance is high, that means eigenvalues are small. So now it's clear that these three quantities, these three ideas, small eigenvalue, high linear dependency, beta have high variances, they are all related. To be more precise, if any one of them is true, the other two are true. So if I say my X prime X matrix has small eigenvalues, that means beta must have high variances, there must be high dependency. So if I know that there is high dependency among the regressors, then the eigenvalues will be small, beta will have high variances. Okay, so that's what we can deduce from all the results that we have learned. So, so I've completed chapter 9 now. So we have one more chapter left. We can start after five minutes break. So one question actually remains is how well does this principal component regression works in estimating or in extrapolation for the acetylene data. You know, that is in the last tutorial. Maybe I'll show you the result after 5 minutes break. I ask you to try out the principal component method for the acetylene data, and then compare the fitted value of these three approaches in with respect to the fitted value. So we have already seen the comparison between ridge regression and ordinary least square. You know, the one that we learned earlier is called ordinary least square. Then we learned ridge, then we learned principal component. So we found that ridge seems to give better extrapolated values than ordinary least square, because at least they are non-negative. Ordinary least square did very poorly. That's because the variance is large, so it did poorly. So by reducing the variance, ridge regression did much better. It won't give you a nonsensical answer. So how about principal component? So as I say, ordinary least square is like taking Panadol to cure your tumor. I don't know about REACH, but principal component is really an operation to remove the tumor. Yeah. So this is really removing dependency. And how will it perform compared to REACH regression? Remember, when we look at REACH regression, we think the extrapolated value are quite good, but we don't know whether it is good or not, right? So you need to do some experiments at those points to confirm it, or you can look at a completely different method and see if you can get similar answers. If you can get similar answer to the REACH regression, then maybe REACH is also doing very well. So here would be all the values. So if you do it, if you do your tutorial, so these are the observed value. You need to compare with this. So this is principal component fitted using the regression coefficient obtained using this method. This REACH, this is ordinary least square. As you can see, they are very close. They are very close to the observed value. 29.5, 29.7, 29.8, 28.9. Very close. In fact, all are doing very well. 20.5, 21.8. In fact, these three are exactly the same, up to the first decimal, and so on. So all three are good in predicting the response or the conversion within the range of experiments. So outside the range, there's no data because no experiment was done. And so this is ordinary least square, the predicted conversion. As I say, the conversion cannot be a negative number. So you know, ordinary least square perform poorly. See, all this nonsensical. Why do these values happen? Because the variance is large, and so it can lead to nonsensical answers. Here you use a bias estimate, but the overall mean square error is still much smaller than this. So it gives you at least reasonable fitted value. Look at this principal component. 35.3, 33, 30.8, 31, 33.7, 33.8, 30.6, 27.1. Looks like REACH regression, which is a very simple idea to strengthen the REACH, give you almost as good result as the much more sophisticated surgical method of principal component. From this comparison, I'm very impressed with the REACH regression. Very little effort, just strengthen it, and then you got good result. Look at this. How much theory we went through, yeah, and we got this. Almost the same. Of course, if you use R, you can do principal component as easily as REACH regression. So which one to use? Well, if I look at these three, I probably won't be using this model. This is not a good model. This one, either this or this. Either one I think is fine. Personally, I prefer principal component. If there's any difference, I think this is slightly better. Yeah, knowing that I've cut out the tumor to get this. Yeah? So, let's go on to chapter 1. So let's see where we are. So it has been a long journey since August. It's about 4 months journey. We started knowing nothing about linear regression. Now I think you know quite a bit. We know what is simple linear regression, multiple linear regression, and then there are 2 special types of linear regression, polynomial, indicator. And then we need to know how to do model adequacy checking, and then how to deal with whatever adequacy problem that we find, and then diagnostic for leverage and influential points. Those points cause problem, yeah? And then multicollinearity is the worst problem for regression. So we deal with it in this chapter, pretty thorough, from some simple method by deleting a regressor to the most complex principal component regression method. So finally, we are now at chapter 10. So when you perform an experiment, you might have 20 regressor variables. And now, not all 20 are useful. We want to select a subset of these for our to be the final model for prediction. You can include a lot of variables. There's something bad with a large model. The variance of your fit value or your prediction, your predicted value will be large. The larger the number of regressors, the more variability it is in your predicted value. So we want a model as small as possible and yet include all the useful variables. So that's the purpose of chapter 10. Where's my chapter 10? Here, okay. Chapter 10, right here. So, in this chapter, we talk about model building, variable selection problem. Before we go on to the few methods, that will help us to select a subset of the variables, we need to do some study. Some of these are theoretical knowledge that will be useful for us. So let's define the problem. So model building means selecting a subset of the variables. So in practice, as I say, there are many possible regressor variables. Only a few are important. And we want to pick them out. Yeah? And this problem is called variable selection problem. Now, there are 2 objectives. And these 2 objectives are conflicting. Number 1 is we want to include as many as possible so that we don't lose anything, we don't skip any variable that is important. And at the same time, we want as few as possible, because a simpler model is always preferred. If I have a model, 3 regressor variable, and on the other hand, I have 20 regressor variable, if in terms of R squared both are similar, let's say, or everything looks similar, I prefer the 3 regressor model. It's simple. And the one important fact is this: the variance of the predicted y increases as the number of variable increases. Yeah, the more variable you have, the less accurate you are in prediction. So, so it's a compromise. So this process is a compromise. Yeah. Now, then for the next few slides, we want to try to understand the full model and the subset model and differences between them. And I try to follow the notation of the books, but there is a bit of inconsistency in the notation. Here, they started to use capital K when we use small k, so it's okay. That one is not too big a problem. So we have our usual multiple regression model. K regresses. I can write it this way. All right. Then we assume that we always have this beta naught, and so P is the notation that has changed now. In our discussion before this chapter, P is just K plus 1, all right? But here, P is used slightly differently. I don't know why the change in notation, but I want to stick to the textbook so that when you read it, at least you won't get confused. But note that the notation now has changed. P is not K plus 1, but P is K plus 1 minus R. So what is R? R is the number of regressors that are deleted from the full model. So P is now the number of regressors retained. Yeah? So the full model can be written as this: xp times beta p plus xr times beta r. So this is deleted. This is, you delete this and you get a subset model. You delete and you get a subset model. So this is your subset model. This is your full model. So this is your full model. So beware of the notation. All right. So let's try and understand some of the theories regarding this full and subset model. I am not going to look at the proof of any one of these, okay? I think this is beyond the scope of this course, but we'll just look at the result. So for the full model, the least square estimates is x prime x inverse times x prime y. There's nothing unusual. So I use beta star for the full model. Sigma square is the same. This n minus k minus 1. So this is the estimate of the residual variance. For the subset model, you know, it's only based on xp, so you can have a similar expression. Nothing interesting here. So here is really the comparison now between full and subset model. So we have a full model, we have a subset model, and it can be shown that the expected value of beta hat p, that means for the subset model, is equal to this. And in general, this subset model, this estimate, beta hat p, is biased. It is a biased one. So if you have a full model, you reduce it, your regression coefficient become bias estimated. Unless this part is 0, unless this is orthogonal to this, those that you deleted are orthogonal, then you will maintain the unbiasedness. What about the variance? Okay? Variance for beta P for subset model is this. Now, variance for the full model is this. Now, if you just look at the variance of the full model for those P regression coefficients only. So this is for everyone. So just look at this for the P only. Now this is a matrix, this is a matrix, this is positive semi-definite. That means the variance of the least square estimate of a parameter for the full model is actually greater than or equal to the variance for the subset model. Okay, so that's a result that we need to know. So for full model, the variance is larger. Yeah? Okay, result number 3. Beta P is a bias estimator, but for the full model, it is unbiased. Therefore, we want to compare mean square error, because one of them is biased, one of them is unbiased. So it makes more sense to compare mean square error. So again, mean square error can be shown to be this. And if you look at this is a mean square error for the full model, for those parameters only. Because it's unbiased, so mean square error is the variance. Again, this is bigger than this. It's positive semi-definite, if this result is true. So under this condition, we know that in general, the variance for the full model is usually greater than that of the subset model. So in other words, subset model, although it's biased, it has smaller mean square error. Next is the estimate. So for the subset model, we already proved in chapter 3 that the estimate sigma square for the full model is unbiased. But for the subset model, it is not unbiased. It is actually biased. So that's another thing to know. So now, next is we talk about prediction or fitted value. So for the full model, we are going to use x prime beta hat as strict, and it is unbiased, and that is the variance. For the subset model, it is biased unless this part is 0. So there is a difference, between full model and subset model. So this is the variance. This is a mean square error. So, so from this result, we can conclude the following. Number 1, y hat is biased. This is a subset model. Subset model is biased unless this quantity x prime p a times beta are 0, which is only true if this is orthogonal. So if you have orthogonal columns, then it is true. And then in terms of mean square error, you can also show that the variance of the full model is usually greater than the mean square error for the subset model. I think the most important message is this: the predicted value of the subset model will have a smaller variance than the full model. So that's the reason why we want to keep our model as small as possible. We want it large enough to include all the useful variables, but at the same time, we want it to be small. Because small means what? Smaller variance in estimation. So, these are all the theoretical properties concerning full model and subset model. I do not want to get into any of this theory at all, so you're not responsible for it. I guess the main message is, if you have a subset model, your regression coefficients are biased, but your predicted value will have a smaller variance. Yeah, so it has some positive things and some negative things. So you can take a look at this theoretical result. I think I will talk about 4 methods for choosing a subset, a proper subset of regressors. Yeah, one of them is all possible regression. You know, you can do all possible regression and then choose one that you like most. Or you can have stepwise regression. One is forward, one is backward, one is stepwise. So I'm going to discuss these 4 methods in the very last lecture this coming Thursday. All right? So I'm going to stop here now, and I will see you this Thursday for the last lecture.